Here we have a picture of a uniform disk, representing a uniform disk, of radius r with a total mass m. And we want to find the total moment of inertia of this disk. We're going to approximate the total moment of inertia as follows. We're going to divide the disk into a central disk and two rings. The central disk has a radius of 1/3 r. The first ring has an outer radius of 2/3 r, of course an inner radius of 1/3 r, and the third ring goes from an inner radius of 2/3 r to an outer radius of r. Now, by using a little bit of proportionality, we can see that this inner disk, whose radius is 1/3 r, comprises 1/9 of the total area because it has 1/3 the radius, and by proportionality, since area is pi r squared, the area is going to be proportional to the square of the radius. And if we square a 1/3 proportionality, this is 1/3 of the radius, 1/3 squared is 1/9. So we've got 1/9 the total area in this inner disk. So we say that the mass of the inner disk, the disk of radius 1/3 r, is 1/9 the mass of the whole disk. We're going to represent that by 1/9 m. Similarly, we can say that the mass of a disk of radius 2/3 r is going to be 2/3 squared, or 4/9 the mass of the entire disk. So that if we want the mass of this ring, we would simply take that 4/9 of the total mass and subtract the 1/9 of the total mass, and we'd have the mass of the ring. That is, we subtract the mass of the inner disk from the mass of the disk that goes out to 2/3 r, and we get the mass of this ring. And we summarize that here. We say that the mass of the disk of radius 2/3 r is 4/9 of the total mass of the whole disk, 4/9 m. And then we go on to look at the entire model. We have an inner disk, radius 1/3 r, mass 1/9 m. The second disk, radius 2/3 r, the ring that goes from radius 1/3 r to 2/3 r, will have mass 4/9 m minus 1/9 m. That's the mass, again, of the disk of radius 2/3 r minus the mass of the inner disk. And that's going to be just 1/3 m if you do the arithmetic here. And then the mass of the outer disk is the total mass, m, minus the 4/9 m that's in the disk of radius 2/3 r, and that's going to be 5/9 of the total mass. Now we set up our model as follows. We're going to make what we call a three-hoop model. We assume now that we simply collapse all the matter in this inner disk into a ring whose radius is half that of the disk. Now that's not precisely what we ought to do to get the actual accurate moment of inertia, but it's going to be our approximation, and it's going to turn out to be pretty accurate. Okay, so we imagine taking this 1/9 m and collapsing it into a disk whose radius is half of the 1/3 r, or 1/6 r. Okay, and we can see that over here. We say that we got a radius r over 6 and a mass m over 9 here. And now this is a hoop. We've collapsed the disk into a hoop. And then we collapse the second disk, or the first ring here, between the 1/3 r and 2/3 r radii, into a hoop that's halfway between these radii. So we're going to take the 1/3 m here and put it in a hoop that's halfway between 1/3 r and 2/3 r from the center. Halfway between 1/3 and 2/3 is 1/2. So our model is now going to have a disk of radius 1/2 r and mass 1/3 m. And then we're going to do this similar thing for the outside disk. Between 2/3 r and r, the halfway radius is 5/6 r. So we're going to take the 5/9 m and put it on a hoop of radius 5/6 r, as indicated here. Radius 5/6 r, mass 5/9 m. Then we can use a three-hoop model and simply add up our moments of inertia. The moment of inertia for each is its mass times the square of its radius. So we have the masses m over 9, 1/3 m, and 5/9 m. Of course, these do add up to the total mass. And the radii r over 6, r over 2, and 5r over 6, each squared. We do the arithmetic and we end up with these fractions. We put them all over the common denominator, 324. We add them up, and we get a total moment of inertia of 158 324 mr squared. Now let me note that if we double 158, we get 316, which is very close to 324. So this is very close to half of mr squared. And it's going to turn out that half of mr squared is really the accurate moment of inertia for a disk, a uniform disk of mass m and radius r. So we've gotten a very good approximation here, good to within just a couple of percent.